the statistics in meteorology has the same characteristics as dynamics. The mathematics is not the main problem. Actually, the mathematics in statistics, at least in the examples I will show, are in the 3 coming lectures, are quite simple. But again, it's what they mean that is a problem. And in this part I will talk about probabilities, which is of increasing importance both for weather forecasting but also to understand the atmosphere. And there are, to make it even more complicated, there are 3 types of probabilities. One is the classical, the frequentist, and the Bayesian. And the classical applies to throwing a die, 1, 2, 3, 4, 5, 6 dots coming up, or a coin. So what is the probability of having 4 throws of a coin and having the head coming up all the 4 times? That is a classical probability. The frequentist applies to an analysis of historical data. So for example, the rain probability in Petersburg or Moscow is the number of rain days divided by 365. So this is type of frequentist probability that you arrive at. And the Bayesian or subjective or degree of belief is when you subjectively or quite so intuitively try to put a probability on an event. I will come back to this aspect much more because it's, I think, very important in today's meteorology. The first, about the classical definition of probability, is interesting also from a cultural aspect, because it started as an understanding of games. People were playing games and they wanted to know what was good or bad odds. The strange thing is that this only became science in the 16th or 17th century. Although people have been playing for millennia, perhaps a million years since man went away from the apes. And there are all kinds of historical evidence that we were playing games long time ago. So why did probability not emerge as other scientists, as other sciences already in the antique years? And so the problem seems to be that people did not believe in randomness. Things did not happen by random because everything was decided by somebody, God, Allah, whoever. So it means that there was no luck or bad luck. It was that if you had been a good boy, he would favor you, and if you were a bad boy, you would be punished. So nothing happened by random. So that's why there was no science. It was to follow his advice, and then you would probably, hopefully, do well at the game table. And it was only during the Enlightenment that scientists started to speculate, or at least scientifically attack this randomness problem. There had been attempts already in the 1500s or 1600s, but they were on a more elementary level. It was advising players how to play, but in the 1700s it became more a systematic science, how to deal with randomness. And a defining moment in all this was the destruction of Lisbon in 1755. There was a severe earthquake outside Lisbon that set off earthquakes in Portugal, but also a big tsunami that almost destroyed completely Lisbon. And then people said, well, whatever the Portuguese have done, they don't deserve this punishment. So God cannot possibly be that evil to do this to the Portuguese, whatever they have done. And that sort of started a debate. Perhaps God cannot decide everything. Things are happening without his will. And then came this, that things happen by random, like earthquakes. So about from this time, the notion that things happen without any divine or other cause came into being. And that started off a more serious scientific investigation into the nature of randomness and of probabilities. So that is why the science of statistics is very young, and also the notion of probability is quite young. That might be one reason why we still struggle to understand what it means. The second definition is the frequentist definition I mentioned, and in metrology we meet that in statistical calibration, the one I talked about with Kalman filtering, also climatological investigation, the risk of thunderstorms in Moscow or severe storms in Odessa, or verification of forecast, where you collect a lot of forecasts and see how good they are, in particular forecast of probabilities, and this is the famous Brier score, which you use to verify probability forecast. And also when it comes to this aspect of drawing conclusions from observations, it took a long time. So Isaac Newton, Galileo and Johannes Kepler had no idea about statistics. So when they measured something, they took the observation they thought was the best one. And they didn't understand that the best thing is to take many observations and make an average. They thought that doing that you would add the errors. And also another problem was that the average might not agree with any of the observations. So for example, if you were an astronomer and you measured the position of Jupiter, you made 3 observations, and then you selected the one you liked most. Because if you took the average, it might be a position where there was no observation. So that was seen as a disqualifying this value. It did not represent observation. So, but in the late 1700s and early 1800s, there became more serious discussions about this statistical inference, and at that time Gauss actually formulated the law of root mean square error estimation and put estimation theory on the firm's theoretical ground. But that was only 200 years ago. And there were also philosophical discussions about the mean, the value of the mean. And for us it was obvious, but it was not obvious for people 250 years ago that the mean is the best estimate. And then finally, the subjective or Bayesian probabilities, they measure our degree of belief. And I will come back to this example, because if you are watching a football match between Sweden and Denmark, and it's 10 minutes left, and or 12 minutes left, and Sweden is in the lead with 1-0, and then perhaps a Norwegian comes into your room and says he bets 1 to 100 that Denmark will win. Then you must form an opinion. Should I accept the Norwegian's bid or not? And then you have to judge this lead of Sweden. Is that just because a Danish own goal or bad luck, but the Danes are actually playing better? Or should the Swedes actually be 3-0? So you have to make a mental evaluation of the football match, and if you should or should not accept the Norwegian's bid. And all this is done completely intuitively. You can't rely on 50 matches between Sweden and Denmark and compute the fractions when Denmark in the last 12 minutes have won. You must form a subjective impression. And some statisticians look down upon that because it's not strictly mathematical, and it's true. But on the other hand, it avoids some pitfalls. And here is a famous example of where frequency statistics fail, and it's the risk with the Concorde. For a long time, Concorde was seen as the most safe airplane in the world. There were no accidents, and then in about 5 seconds time, in the terrible accident in 2000 in Paris, a Concorde changed from being the safest airplane in the world to the most unsafe, because now it had one accident, and the number of flight hours, if it's 100,000, I don't know, but it was much less than other companies, meant that suddenly it came in the top in the accident league. And of course everybody feels that this is not natural. Obviously there was a risk before the accident that there would be an accident. So and a Bayesian approach, if it had been applied, meaning that somebody before this accident sat down and looked, what can go wrong with Concorde subjectively, would have reached a very small probability, but still something more than zero. So the Bayesian approach avoids this unnatural change from one extreme to the other. And there are more examples where this frequentist approach fails to give realistic values. So this is the Bayesian approach. And I will stay with that because it has a lot of applications in metrology. The classical probability is if we now have a sack of green and brown balls, and we call the green balls rain and the brown balls dry, as a simulator of a probability, average probability of 30% for rain. And then and there are millions of these balls, so nobody will notice if a few of them are missing. It will not change the proportions. So now if we select 3 balls, they can all be rain, or they can all be dry, or 2 of them can be either or. And we can calculate exactly the probabilities for each outcome. But as you can see, it's only 44% likely that we will get a proportion of balls that agree with the general picture. 56% chance that we will, by these 3 balls, get a misleading image of the proportions. But this is the classical approach. Now the Bayesian approach is the reverse. We have a sack of green and brown balls, but we do not know the proportions. And then we select 3 balls at random, and 2 are rain and 1 is brown. And then we want to know what are the probabilities. What conclusions can we draw from this very simple and of course not very realistic sampling. And this can be explained by Bayesian statistics. And now I must make a break just to check that everything is yes. Because it's okay. So now I go back to this can be explained by Bayesian statistics, and the name Bayesian comes from a priest in the 1700s in England who wrote a very interesting paper about this, and after him he was called Thomas Bayes, and that's why it's called Bayesian. And the way he wanted to present his ideas is very appealing to me, and actually it's another case where the original paper sometimes is the best teacher, like the Coriolis paper from 1835 was the best teacher, to me at least, of the Coriolis effect. The Bayes experiment in the 1700s also served as a good illustration to what he had in mind. So he has a billiard table, and here is now the billiard table, And the classical approach is that you draw a line covering, dividing the big billiard table into 70% to the left and 30% to the right. And then you throw a billiard ball, and you can then calculate the probability that it will stay on one side or the other. And throwing 3 balls, you can calculate in advance the probability that all will be to the right, all will be to the left, or a mixture, just in the previous example with the sack. But Bayes did something else, of course. He first of all threw a ball, and standing with his back against the table. So he threw the ball over his shoulder or behind his back, and did not see where it ended up. So somebody else with a chalk drew a line. And then Bayes continued to, let's say now, threw 3 balls, and not seeing where they ended up. He was just told if they ended up to the left or to the right of the line. So in this case, he was told twice to the left and once to the right. And then the question is, from this experiment, what can we draw, what kind of conclusions can we draw about the position of this right line? And this is the Bayes rule. I will not go into the mathematics. You can easily find it in any statistical book, but it's just to show you how simple it is. But the calculations to get the answer is a bit more complicated. And what you get is something like this. It's the probability of the position of the line. And the most likely position is somewhere 3/4 from the left. But there is also small probabilities of the line being in the very extreme. So it gives you a best estimate, but also the possibility of the line having other positions. And of course, it's just by 3 experiments. If you do more experiments, of course, this curve will be sharper against the true value. So now it might be with more experiments that this will get more sharp and this will go down. On the other hand, we can't exclude that the line is here. And then the curve will shift gradually after every new experiment. But in every case, tell us about the most likely position, but also the probability of more extreme positions. They cannot be excluded. And that is an important experience from the Bayesian statistics. You can never be 100% certain. There's always a small chance that something extreme will happen, like the Concorde accident. Now back to the football match. So here we have a situation where it's 12 minutes left, and here is the probability that Sweden will score more than Denmark, probability of a draw equal, and probability that Denmark actually in the end will score more than Sweden. So based on this man will accept or not accept the Norwegian offer about 1 to 100 that Denmark will win. But then suddenly something might happen. There's extra new information, and Sweden scores a goal. And that of course will highly increase the probabilities that Sweden in the end will win. And now there's only a marginal chance for Denmark to win in the end, but it cannot be excluded. So now it's even less likely that Denmark will win. Now this is how people would act mentally in the case of a football or ice hockey match. But it's also applicable to metrology. So here we might have some methodological parameter, and the probability that it will be normal weather is here, but for different reasons we think that something wetter than normal or cooler than normal will occur, but we can't exclude that it might be drier or colder than normal. So this is our preliminary feeling about the weather. And then something happens. We get a forecast from a computer, for example, or an observation comes in, telling about approaching rain or radar images. So here is an observation or forecast, and this of course affects our probability distribution. We are more certain now about, but still we cannot exclude in the end that the opposite will happen. So this is how the mental brain works also in meteorology. And as it so happens, this also applies for very advanced systems in numerical weather prediction, like data assimilation, observations entering into the computer to map, to analyze the current weather systems. Then the same type of logical reasoning is done by the computer. Thank you.